welcome to the pre-video for lecture 3. We're going to talk about calculus, because calculus is how we do learning. We're going to be doing optimization to make our machine learning systems predict better. And that requires finding the tangents of stuff in matrix land. So let's get into it. So we need a data representation that is in matrix land. We have been so far talking about our training data as a data set, but to do learning, we need to do matrix algebra. And that means turning our data sets into matrices. So over here on the left, we've got a feature vector. This is the vector for a single data point. So if we have m variables in general, our single data point, note the lowercase bold, right? That's a vector, okay, because it's a lowercase and bold, and it's representing a single data point's variables. Okay, well, if we're going to represent an entire data set, the way we do that is we take each data point and we put it into a row. So we transpose that column vector, make it a row vector, and we fill up a row of data with that data point. And then we do that again for data point number 2, and again for data point 3, and so on up to n. So if there are, this many features, this many variables in the data set, m features, and we have n rows, that means n data points, then our design matrix fills up like this. It's going to be n rows for the n data points and m columns for the m features. Okay, that's the generic view. Let's do something very specific. So what if we have this data set? So reminder how our set notation works. We were given a data set of pairs of inputs and the correct labels. We have n such data points. We have n data points where each data point has got a vector of x's and the correct label for it. In this case, we're doing binary classification. Our outputs, our correct labels, are either +1 or -1. So the data in this case is the kinds of measurements we might get at a doctor's office. A patient is here in a row, and this patient is age 22 and male, and these are the weight and height of the patient. And this patient is negative class. Let's say that negative class means the patient is healthy. And this patient is positive class. That means that that patient has diabetes, let's say. So we just take this matrix that we wrote here in a table, and we just exactly make that our linear algebra design matrix, right? We've got patients on a row, and each column is one of the variables. Note that we took the categorical variable of male or female, and we turned it into a one-hot encoded setup, where 1, 0 indicates male, and 0, 1 indicates female. Okay. So we want to predict outputs. We want to have a machine learning system that takes the inputs, the x variables, and produces output predictions. So this is the true labels that we want the machine learning system to do. This is the x inputs. And let's just assume we have some weight vector, some set of parameters that our machine learning system has already learned. So what does predicting look like? Well, we have our data inputs, we have our weights. The predicted outputs of our machine learning system are just x times w in matrix land. So the x rows are x, the x has n rows because there's 3 patients, so there's 3 rows. So that means there's going to be 3 rows on the output, right? Matrix algebra. The W vector is a column vector. It's one column wide. So that means we're going to get one column out with 3 rows. That is, we get a prediction that's the number of patients long in a column vector, right? That's exactly what we want. We want the output to be per patient each row. So we're predicting the patient's status, whether they're diabetic or not. So this matrix multiplication in here produces some real numbers. And those real numbers, well, they're not the categories. So usually we take this output and we run it through some kind of threshold to produce clear categorizations. Like if the threshold over 0, then we're going to make this a positive class. And if it's under 0, then we're going to make it a negative class. Okay, another thing to note here is a notation here. Note this is y hat. Y hat. The hat means estimated. You'll see this again and again in statistics. A lot of statistical variables will have the hat notation in many authors' work, where the hat means, hey, I'm predicting this. I'm estimating this. This is not truth. Previously, truth was just y. Y hat is our guess, our estimate. Okay, so as I said, we will typically take this estimated y, and we're going to run it through some function, like a threshold. Okay, and the threshold is going to produce our categorization. So f of y is something like, hey, I'm just going to say, if you're over 0, you're positive class, and if you're under 0, you're negative class. So that's the f here. It's just some threshold. Remember that y is the truth. Y hat is our estimate given our inputs and our parameters. So we can define something called a loss function, or you can think of it as counting up errors, right? The difference between the truth y and our predictions, which is f of y hat, that is how many mistakes we made. If our predictions always exactly match the truth, then this vector in here is a 0 vector, right? If there's no difference between the true values and the function that we run this through to make our predictions, then perfect. We did perfect. Our predictions exactly match the truth. We have 0 loss. If, on the other hand, we made a mistake, like if we called this patient here actually negative class, if this was a minus 0.65, then there would be a 1 here and a minus 0.65 here, and 1 minus, not 0.65, because we'd go through a threshold, so this f would make it -1. So it'd be +1 minus a -1. So there would be a non-zero entry here in our loss. Okay? Now, note that y hat is really a function of x and w, right? So we can just replace y hat, our estimate, with xw here. Okay, so this is our loss function. Our loss function, note, is a function of the weight parameters. This is going to become critical to us in a second, because the weight parameters, those w's, that's what we're dialing back and forth. Those are the things that our machine learning system is learning. It's learning those weights. Okay, so remember, machine learning is really just picking a model and then minimizing a loss function. Well, we just defined a loss function. So what does that look like? So here we go. Our loss function is the true value minus our predicted value. Okay? So if we parameterize a graph like this, where the 0th element of the weight vector is over on this axis, and the first element of the weight vector is on this axis, and our total amount of loss or error is on the vertical axis, right? So that says as we try different weight values, right? Like if our weight is currently W sub 0, and W sub 0 lives right here on this surface of loss, okay? So the left side graph is a three-dimensional view. The right side graph is supposed to represent a two-dimensional idea of the same kind of graph, but with like a topo map. If you've ever used a topological map when you're going hiking, right? These curves here show equal height, all right? So everything on a curve is at the same height on the graph, and the lowest parts of the graph are down here, right? That's the center of the conic section that we're showing you. Right? This is kind of cone-shaped. Right? So that's the low cone, and this is the high outside part of the cone up here in the red territory. All right, so at a particular choice of weights, we are going to have a particular level of error. So right now, our weight value is this one, and so that's going to correspond to this point on our graph. Well, if we're learning, what we want to do is we want to make fewer errors. Fewer errors are down here in the center, right? We want to be at the bottom of this cone shape. That's where we want to be. So what we're going to typically do with learning is we're going to move our weight choices, we're going to change them to move towards the center of this conic section. We want to move towards the minimum of this function. We want the minimum of the loss function. How do we do that? Well, with calculus, because when you have anything, any kind of function, the tangent or derivative of that function shows you the direction to change, right? As we move our weights, we want to move them towards this low point. What's the direction towards that low point? Well, if we're starting off up here at W0, then the tangent line of this conic section is going to show us which direction to move our weights. Okay? Looks like this. So we know we want the derivative of the loss function with respect to the weights, right? That's going to be the tangent of this conic section, the derivative with respect to weights. So if that is going to tell us which direction to move, that's going to, be a very important thing to calculate. So I'm going to introduce some notation here. The partial of a function with respect to a variable, you're probably used to writing it like this: partial of L sub w with respect to w. I'm going to introduce this notation. This is called a nabla symbol, and it just means the partial of this function with respect to its parameter. Okay, it's a shortcut. This is just a notation to say partial derivative. Okay, this nabla thing is also called the gradient. Okay, so this gradient is the derivative, the partial derivative of L with respect to W. That's the gradient. Now, hey, let's look at our loss function. Our loss function, well, y is not a function of W. So because it's not a function of W, the partial with respect to the y term here just disappears, right? What we've got is the function part. That's a function of W. Nothing else is. So when we take the gradient of our loss function, it's really just the negative gradient of our predictions. Okay? The negative gradient of our predictions is the direction that we want to move. It shows us that tangent line, that negative gradient, is the direction to step to minimize our weights. So if we take a small step in that direction, then we will get to a new weight value, which is better and lower loss. We went from here on the 3D surface down to here. Okay, well, we're not all the way at the minimum yet, so maybe we do this again. For this new weight, so this is time 0, this is time 1. We now have this weight value. Let's take the gradient for this weight value again. We get a new direction to step. We go a little bit in that direction, right? This is a direction vector. How far we move on that direction is up to us. And we keep doing that until we reach the minima. And that, my friends, is machine learning. Okay, we've changed our weight values iteratively until we reach the lowest part of the loss surface. Okay, so clearly, because we're doing tangents, derivatives, we need calculus. Just a reminder of some really basic calculus. If you have a linear function and you take the derivative with respect to a variable on the right-hand side, well, just a constant. The tangent line is the slope, right? A. If you have a quadratic function where there's an x squared term, right? Basic calculus, the x squared, the exponent comes down, and you now have a 2ax and a constant. Okay, so that's this tangent. You have a tangent there. All right, but that's just one variable. We're doing stuff in matrices, so we've got to do partial derivatives with respect to vectors and matrices. So if you've got some vector and you take the partial with respect to a scalar value, that's super easy. You just take each element of the vector and do its derivative separately with respect to the scalar. If you have a vector and you're taking the derivative with respect to another vector, okay, well, the result is now a matrix where the columns represent the y's. Okay, so this is all with respect to the first element of the y vector. And this is all with respect to the mth element. And the rows represent the x elements. So this is with respect to the first element of x, and this is with respect to the nth element of x. Okay, what about matrices? So if we take the derivative of a vector with respect to a constant matrix, where the matrix is not a function of the x vector, well, that's super easy. It's just the matrix itself. Now, I want to introduce you to two separate notational forms. The numerator form looks like this. The denominator form looks like that. The difference is merely the order. So this is matrix first, then vector. This one's vector first, then matrix. And if you remember from linear algebra, you can switch the order of things in a matrix multiply by transposing them both. So AX is equivalent to X transpose A transpose. Okay? So denominator form is, it's just convention, right? You need to decide which way you're going to write these things. And we're going to use denominator form convention, but you will probably see other things out there when you're looking at this stuff that's in numerator form because somebody else made a different choice. In this class, we're going to assume denominator form. Okay, if you look on Wikipedia, you can find a nice little table of many kinds of vector derivatives that you may need. All right? Of note, maybe a chain rule situation. Woot, woot. Chain, chain, chain. Chain of fools. Okay, that's enough of my singing. So, matrix by scalar. So we need to take derivatives of matrices, not just vectors. And, well, just like with vectors, the derivative of a matrix with respect to a scalar is going to be very easy. It's just take the matrix, do every element individually. Okay, matrix by vector looks a little bit different. So in matrix by vector, what you're going to see is we have, in our denominator form, where we do vector, then matrix, right? Whoops. Hello. Why are you bad? Okay. Got myself messed up here. Sorry. So you're going to, when you break this down, this is just a matter of doing the actual algebra, right? Matrix algebra. So think of this as this is a variable. So we're taking the derivative of A with respect, the matrix A, with respect to the vector x. And in this case, it's a function of x squared, right? Like if you're in scalar land, there's two x's here. So x transpose ax means that there's two x's. That means it's a vector x squared situation. And it's just the rules of matrix algebra that tell you that you've got to break up that x squared into an x transpose in front of the matrix and an x on the back of the matrix. Okay, that's just matrix algebra when we're in denominator form. Well, because this is an x squared term, the derivative with respect to x produces, just like in scalar land, if you had something x squared, the derivative is 2x. So we have 2xt, and then the matrix. Okay? And then the form of this just looks like the matrix algebra. You can find that out from doing that. Okay, again, there's a nice little Wikipedia page with, if you need to take derivatives of matrices, might be very helpful. Okay, so like I was just trying to show you just now, if you get confused about doing anything with vectors or matrices and derivatives, just stop and think about this as if it was a scalar. Once you understand what it would look like if it was scalars instead of a vector or a matrix, then you can go back to think about the row columnness, right? And that the first element determines the number of rows and the second element determines the number of columns. And then that will get you to the shape of the output that you know you need, right? Like we need to have the right number of rows to represent the right number of data points. Okay, that's it. I will see you all in class. See you soon.